Hello and welcome to Sarat Chandra IAS Academy, where your dreams are our mission. This is Yatharth here. Today we'll be talking about Earth's heat budget as well as NASA's CubeSats. So, Cube and Sat, you can see a cube-like satellite here. So we'll see what is NASA, and what are the CubeSats, what is their relation to the Earth's heat budget. All right, and in a larger view, what is their relation with the climate change. Okay, so as you can see now, even in India, just imagine this is India. All right. So in Kerala, we can see the monsoon has arrived. The monsoon has arrived. While the Tamil Nadu is still stays in the rain shadow region. You can see floods happening in the northeast area, while heat waves coming here. Also, there is snowfall in the areas in let's say upper areas where it's not supposed to happen right now at least. Okay, there is heat fall in this area, heat waves in this area. So this all is a impact and effect of the climate change. All right. We can also see the reversal of the El Nino to La Nina now. Strong events. We can also see Cyclone Remal here. Okay, in the Bay of Bengal and this side. So these are all impact of the climate change. So this is related, the CubeSats are related to that only. Okay, to our heat budget only. So let's talk about the Earth first. Because this is the planet we are living on. This is the planet we are talking about. So we must know about this. This is our lovely India here. Okay, and you can see two poles in not in the picture, but there are two poles to the Earth that are the North Pole as well as the South Pole. Okay, South Pole we know as Antarctic. Recently we talked about Antarctic a lot. Okay, the Antarctic Treaty, we talked about that. So can you in the comment section tell me what research station India has in the Antarctic? Okay, was it what is the name of that? It is related to Gangotri. Okay, all right. Now let's talk about the Earth itself. So in the solar system, the Earth is the third planet from the Sun. Tell me what are the two more planets? Okay, then the age of the Earth is almost 4.6 billion years old from the formation itself. Then the average diameter, we are talking about the diameter, not the radius, please remember. Okay, I hope you all know what is the diameter. Okay, so diameter is at 12,742 kilometers. And we talk about the atmosphere, so it's primarily composed of nitrogen and oxygen, that is 21%, with trace amounts of other gases. We talk about the crust, there are three layers: the crust, the mantle, and the core. Okay, core is the last layer or the most internal layer. It is liquid layer of hot metal, mostly iron and nickel. Please remember this, very, very important. Okay, iron, that means Fe, ferrous, and nickel, Fe. You can learn this. Then there is mantle in the between. There is the thickest layer. Please remember, mostly solid rock that is hot and under immense pressure. Okay, this is the layer from which lava also emerges. When we talk about the crust, the layer which we live on, there is the thinnest layer. Okay, solid, that means continents and ocean floors. Now, lastly, we talk about the complete composition of our planet. We see that it is mostly made of iron, furthered by oxygen, silicon, as well as magnesium. Alright, there is only one moon to our Earth that is known as our moon, or it's also known as the Luna. Okay, you must have heard the word lunar mole. Lunar. Okay, lunar eclipse, solar eclipse. So, this is why our moon is known as the Luna. Alright, now let's move to the concept that we are talking about, we are discussing, that is the Earth's heat budget. Okay, so what is budget basically? Okay, let's see here. What is a budget? Just a second. Well, let's do in this. Talking about the budget itself. This pen is not looking good. Let's change it to blue. All right. So budget is something. How much is incoming and how much is outgoing. So balancing this incoming versus outgoing is known as the budget. Okay. Now what we are talking about here? Heat budget. Heat budget. So how much heat is incoming and how much heat is outgoing. Okay, so we cannot control the amount of heat that incomes. Okay, because it is coming from the sun directly. First thing first. And then the outgoing heat, we do not want to preserve a lot of heat. We don't want to preserve a lot of heat because it will make our planet hotter. Okay, so there are only two ways to cool our planet. One is to, let's say, reduce incoming heat. Okay, reduction in the incoming heat or increasing the outgoing heat or increment in the outgoing heat because we would not want our planet to get too hot. Also, this all is, let's say, done by the greenhouse gas effect or the greenhouse effect. Without the greenhouse effect, it is very, very necessary for our planet, the greenhouse effect. Okay, without the greenhouse effect, our overall temperature, the average temperature of Earth would be negative. It would be very, very cool. Okay, and life would not sustain here if not for the greenhouse gases. But the overdoing of this greenhouse right now is making our planet very hot. Okay, so greenhouse gas effect or greenhouse effect is not necessarily evil. Okay, if the statement comes that is all greenhouse gas effect is evil, is bad, completely bad, then it's not bad, it's not completely evil. Okay, it is actually good. It's good. But when we are saying about over or extensive greenhouse effect, this is making our planet bad. Okay, this is making our planet hot. So please remember, greenhouse gas effect is very necessary for Earth. Okay, all right. Now let's talk about the heat budget. So Earth heat budget refers to the balance between incoming and outgoing energy. It is crucial for maintaining a stable global temperature that allows liquid water to exist on the surface, a key ingredient for life as we know it. Okay, so what will happen if the heat increases a lot? Water will evaporate. Water will evaporate. Glaciers will melt, the sea level will rise, there will be disasters and disasters. All right, now we talk about the incoming solar radiation first. Incoming solar radiation. So let's assume this is 100%. Okay, that means sun is trying to throw light on the earth or heat in form of light on the earth or just call it energy. Okay, so let's assume it is 100%. Now what happens to this 100%? Okay, most of it, that means 47%. 47% is absorbed by the ocean and land is absorbed. Absorbed, we can mean that utilized, let's say, somewhere in its system. Okay, we'll be talking about this later, that what happens to the absorbed one. But right now, let's say the most of it, major of it is absorbed. Now, what happens to the second part is that some of it is reflected or scattered. Okay, so some never reaches the earth, it is scattered to the space. That is a very low portion, 7% only. Some is reflected by the clouds itself. Okay, it comes and it does not ever reach the earth. That is 17%. And 6% is reflected by the surface because the surface of earth is also little bit reflective. There is also albedo effect. All right. So now what happened to almost 30% of the sunlight? It got reflected. So 47% we utilized, 30% got reflected. Now remains 23%. This is absorbed by the air, H2O, ozone, clouds, and dust. That means in the atmosphere. In the atmosphere. So let's understand it a little again. Okay. What do we see? Out of 100%, we saw 30% getting reflected and scattered. 47% got absorbed by the earth and or land and ocean, and 23 by atmosphere. All right. Now let's see what happens to this heat. Coming back here again. So talking about the 47% first. This 47% first. Okay. Now via conduction, the 7% of heat is lost again in the atmosphere. Okay, we are not saying that it has completely gone out of atmosphere. We are saying that it is still reflected back to the atmosphere or passed to the atmosphere. Let's say the land is hot. Let's say the land is hot. Now there is a tree. Okay, so tree is also connected to the land itself. Tree is also connected to the land itself. So heat will come from here to here if it's cool. Okay, and then it will go upside. Okay, via evaporation, transpiration, many other different forces. So this is the heat of conduction. Okay, which is in complete connection with the land. Then there is, let's say, latent heat. Let's say there is a building also. Okay, there is a building. Now, if the land is hot, the building will also get hot eventually because the heat will pass through conduction. So, 7% of such heat is passed through the conduction. Second is latent heat. Okay, 24%. Let's say there is an ocean. It is getting warm. The water is getting warm. So, there is a latent heat which is inherently present in the things. This is 24%. And one of the very important one is the long wave radiation. Long wave radiation. So 10% heat is emitted finally as the long wave radiation from Earth's surface. This is very, very important. All right. 6% of this goes of this long wave radiation absorbed by the H2O, ozone clouds, and so on. Okay, now what happens? The heat that is absorbed by the atmosphere or ozone clouds and so on, 20% of it is radiated from clouds, 40% radiated from H2O, ozone, and CO2, and 10% as the long wave radiation. So, mostly what we have this 23% which is absorbed by the atmosphere and 47% here. Okay, so this is basic heat budget that most of the heat that comes to earth is reflected, some of it is absorbed, all right, and used, utilized. So in a perfect balance, what should happen? In a perfect balance, what should happen? That this is so completely lost. Okay, we are not utilizing this one. This should go back. Okay, some of this should go back. 70 to 80% of this should go back, and 47% we see here. So what we see? 100% energy came, 30 got reflected or scattered, 70 we absorbed and used. Okay, most of it through the land and air, 40, let's say 50% approx. Okay, and 20% in the atmosphere. Okay, some of it goes back, some of it does not go back. So 70% we are using. So this is how Earth should be balanced. Now what has happened that this heat budget is not working as intended because atmosphere is having high global warming gases or GHG gases, greenhouse gases. Alright, these greenhouse gases are preventing the heat to go back in the atmosphere as out or outgoing energy. All right. So this is why we are reading about this topic. So NASA has now launched a tiny satellite to measure heat lost from Earth's poles. So we talked about the long wave radiation, long wave infrared radiation. Okay, so we'll be talking about that. First of all, let's talk about the NASA itself. So NASA, also known as the National of the where USA, all right, America, not India. Aeronautics and Space Administration. Aeronautics as well as Space Administration. So it is an independent US agency. It was established in 1958. 1958. Can you tell me in the comment section when was ISRO established? Okay, its headquarters are in Washington, DC. What is the DC here? DC is District of Columbia. District of Columbia. It's a square shaped district in which Washington DC is located. Very small, let's say, capital. Okay, now let's talk about the mission as well as what has NASA done. So NASA has launched this mission known as Pre-Fire. Just a second. I'll write this again. Handwriting did not go so well. Okay, let's use this. So mission Pre-Fire. Okay, so polar radiant energy in the far infrared experiment. So what we are talking about, poles first of all. Poles or polar. So two poles we have. One is the North Pole. One is the South Pole. Okay, these poles mostly reflect energy or emit energy in the far infrared section. So we need to know what is this infrared also, what is the connection of infrared to the lambda, that means wavelength, and energy. E is equal to h mu, the Planck's constant, and the frequency of the wave. And frequency of the wave is equal to 1 upon lambda. Alright, so frequency of the wave or energy of the wave is inversely proportional to its wavelength. Okay, we'll be talking about this later on. Now let's talk about the CubeSats. So on May 25th, the NASA launched one of the two climate satellites, which would study heat emissions at Earth's poles. So they'll be studying heat emission on the Earth poles. Sitting atop in one Rocket Labs Electron rocket from Mahia, New Zealand, the second satellite will be launched in the following days. Okay, so they'll basically be rotating over the poles and see that how much heat is being emitted by the poles itself in the form of the far infrared long waves. All right, and let's talk about the pre-fire mission also. So pre-fire mission is the name of this, let's say, satellite launching mission. So it aims to fill a critical gap in understanding the planet's energy budget by studying the heat emissions from the Earth pole. So basically, two satellites are there, as I told, and both have thermal infrared spectrometers. Thermal, thermal means related to heat. Infrared is the wave or the long form radiation that the Earth is emitting from the poles. And a spectrometer is something that will know that what form of radiation is being released. All right. Okay, now let's talk about the spatial satellites. So these are the CubeSat or cube satellites. So first of all, they look like a cube. What is a cube? Cube is like this. Okay, that means all of the sides are equal and it has 6 faces. Alright, so this is basically cube 1, 2, 3, 4, 5, 6. This is a Rubik's cube. This is a Rubik's cube. So cube satellite are very small satellite. They can also be attached to each other. Alright, this is a 1 unit satellite and these can stack over each other in the 24 units maximum. Okay, the CubeSat has 6 units. CubeSat has 6 such cubes or small cube satellites, and they are very small. Okay, their height is only 10 centimeter by 10 centimeter. Basically, they are thermal spectrometers. All right, and their weight is not more than 1 kg or something. So they can be sent in a unit of 1, 5, 6, 3, 12 or such that. Okay, and these were first developed in 1999. So 25 years later, they are being used here, and they will be put in a near polar orbit. Near polar orbit. This is very important. Okay, it is a type of low Earth orbit, and altitude will be, I'll write it separately, 525 kilometers. So can you compare it to the recent space tourism lecture we saw, and also to the Gaganyaan? Okay, so what is the difference between altitude of these satellites and these two missions? Okay, so this much we have already learned. Now we can see the mapping portion a bit. We talked about the New Zealand as well as Antarctica. So New Zealand here, okay, rocket was launched from here. Then there is Antarctica, very far from here. Okay, not pretty close as we can see in the map. All right, and, we can see Australia also here. Papua New Guinea, Indonesia, and so on. Okay, this is Antarctic. We talked about Antarctic a lot in the last lecture when we talked about the Antarctic Treaty. So you can re-watch that lecture and read about it again. So what happens from the Antarctica, basically from Arctic and Antarctic, North Pole and South Pole, they are very reflective surfaces. So from here, the radiation goes in the form of far infrared radiation. Okay, that has wavelength of 3 micrometer to 1000 micrometer. Okay, we'll be talking about this. and this is sort of infrared electromagnetic radiation, and there is no way to measure this type of energy. Right now, we do not have technology to measure this energy. So this is why there is a gap in knowledge. But we are hoping that these CubeSats will be able to measure this measure this radiation. Okay, now let's talk about all these radiations and all. In very simple manner, we'll try to understand, not going overly scientific. So what we see, just a second. Okay, the wavelength is high here. Okay, wavelength is high here. Wavelength, what is wavelength? Difference between this and this. Okay, so wavelength is very high here, even further high here, and reducing here. Okay, wavelength is reducing here. That means energy is increasing. As I told you already, just a second, that the energy of wave is equal to h mu. Okay, h mu. H mu is equal to h is equal to Planck's constant. This is a constant. Basically, what we say, energy increases as the frequency of wave increases. Okay, and the frequency h mu or mu is inversely proportional to the lambda, that is the wavelength of the energy. So as the wavelength decreases, the energy of the wave increases. Okay, but what it cannot do, a high energy wave, what it cannot do, it cannot travel large distances. Okay, that is the issue. A high energy wave will only travel very small distances as the energy is lost because the wavelength is very, very small. Okay, and the wavelength is, let's say, when the wavelength is large, it can travel high distances, long distances, but with less energy. Okay, so you have to make compromise somewhere in life. All right. Now, what we see, there are radio waves. Okay, the radio waves we listen. So then there is microwave, infrared, visible spectrum. This is the light that we see. Ultraviolet, X-ray, gamma rays. All right. So when you see the radio waves, somewhere, let's say, radio station is transmitting a wave, and it will go further. Okay, you can hear it any distance far. But if you release a gamma ray, then it will not reach anywhere because it is very, very high energy, but will cease to exist within a small time frame. Okay, we talk about the X-ray. So X-ray will only go far, let's say a bit far, but it can also penetrate your muscles, skins, everything. Okay, and obtain your bone data. So this is the energy of X-ray. All right. So can it penetrate Earth's atmosphere? So radio waves, yes, they can penetrate with long, very long distance waves. Okay, these can no, yes, and mostly the high energy waves cannot penetrate. This is why when we talk about the infrared spectrum, just a second, I'll delete this. Okay, so when we talk about the infrared spectrum, we see that it has a long range. Okay, 10 to the power minus 6 and 2. So there is almost 4 powers here. Okay, from 2 to minus 6. Actually 6 powers. All right. So let's talk about this infrared spectrum a bit. We saw that wavelength is 3 micrometer. 3 micrometer to 1000 micrometer. So what is micro here? Okay, deci, centi, milli, micro. Micro means mu. Mu means 10 to the power minus 6. So let's read all this. Nano, pico, femto, atto, zepto, and yocto. Please remember these. Alright, especially till at least nano. Please remember. Okay, then in the increasing power there is deca, hecto, kilo, mega, giga. Giga all know, gigabyte. Okay, tera, petabyte we all know, 10 to the power 15. Then there is exa, zeta, and yottabytes. Now we are talking about the micro. So we see 3 micrometer. That means 3 to the power minus 6 meters. And 1000 micrometers. That means 1000 to the power minus 6. That becomes what? 1 into 10 to the power minus 3 meters. Okay, so this is the length of the far infrared radiation which we do not know about. So what will these CubeSats do? They will measure the amount of the heat. Just a second. So CubeSats, just make a mind map, simple mind map. What these are? 2 satellites, 6 units of cubes, 6 unit of cube on each satellite, 1 launched, 1 not launched right now. What will it do? What will it do? What does it have first of all? Thermal spectrometer, thermal IR spectrometer. What will it do? Read how much long range thermal radiation in the form of infrared energy is released by the poles. Okay, one from the Antarctic, one from the Arctic. Okay, and what is the name of the mission? The name of the mission is Pre-Fire. Okay, this is simple mind map. It will also, let's say, see that how much far infrared radiation is trapped by atmospheric water vapor and clouds at poles, and how it influences the greenhouse effect in this region. So it's all related to the greenhouse effect as well as climate change. And please remember, all greenhouse effect is not bad. Okay, overly getting the greenhouse effect on the earth is bad. So please remember all this. All right, thank you for your presence. This is Yatharth signing off. I'll upload this PDF in the channel also, Telegram channel also, that is Sarat Chandra IAS Academy. So please be on the channel also. Okay, if you have any feedback or any comments, please let me know. Thank you very much. See you again.